Another day in San Francisco means another day at the 2019 AGU Fall Meeting. There's lots of coverage coming your way. AGU TV starts now. Hello and welcome to day 3 of AGU TV. I'm your host, Juliette Goodrich. It's been an exciting first few days of the meeting, but don't worry, it's not even close to winding down. Today, we're interviewing top newsmakers and we're touring top universities and organizations doing cutting-edge work in science. Joining us now is Dr. Twyla Moon, and she is a research scientist at the National Snow and Ice Data Center. Thank you so much for joining us.
Thank you so much.
Let's begin about talking about the next generation of cryosphere scientists and what's in store.
The next generation of cryosphere scientists is growing. There are many more people working on this topic than there used to be, and people are understanding this changes in the different components of the system, but they're also now reaching out and really helping people to connect decisions and environmental planning and business and government elements to what's happening in the changing cryosphere. So we're not just understanding what's changing in the cryosphere, but also how it impacts people and ecosystems.
And specifically, let's talk about the human-caused climate change and how cryosphere scientists are working in terms of connecting that information.
Yes, we're looking closely at the differences that human actions in warming the planet and increasing air and ocean temperatures, how those are playing out in the cryosphere now, but also really importantly, looking at how potential future actions might influence the cryosphere, because there's a really big range between the change that's more minimal that might happen with significant human action and the more substantial changes if we're not following through on reducing greenhouse gases.
Is it challenging right now in terms of communicating this science? How are cryosphere scientists communicating the importance of this science?
That is something that we are honestly learning while doing. There's an increase in appreciation of how important communication of this is, and especially because we're seeing such dramatic changes, and they do impact all parts of the world. And people are getting much more active in talking with their communities, with governments and policymakers, taking to social media, as well as trying to write papers and put forward media that is more accessible to non-scientists. But we're still improving.
What are those dramatic changes, and what should be communicated to those that aren't scientists?
Yeah, well, you can imagine the cryosphere, we're studying all the things that are frozen. Mm-hmm. And so increasing temperatures and increasing in the air or the ocean, that has the potential to melt those frozen parts of the Earth system. And we're seeing that happen with dramatic losses of sea ice in the Arctic, where that number this year was the second lowest on record. We're also seeing a lot of land ice loss, and land ice is what adds to sea level rise. So higher storm surges, more flooding, That's the sort of impacts we're seeing from land ice. And as permafrost, frozen ground thaws, we're releasing more greenhouse gases into the atmosphere and exacerbating warming. So all of the parts of the cryosphere have been changing dramatically because of these increased temperatures, just like taking an ice cube out of your freezer and leaving it in the warmer air on your kitchen counter.
Absolutely. All right, Dr. Moon, thank you so much for your time and information.
Yeah, thank you.
Let's now start our tour of the very best scientific universities and institutions around the globe.
IIHR Hydroscience and Engineering is an academic research center that focuses on hydraulics, hydrology, fluid mechanics, environmental science, and water sustainability. The mission is to provide both fundamental academic research to improve the engineering and scientific community, but also to do applied engineering and really help the engineering community move its engineering design forward.
Historical record, what it suggests is that the frequency of flooding across Iowa and large areas of the central US has been increasing. So one of the questions that we ask ourselves is the increase that we observe in the records, is it due to natural variability or is it driven by greenhouse gas emissions and anthropogenic climate change? The flood of 2008 made us wonder what kind of effect climate change is going to have on flooding over Iowa and over the central US.
For many years we were studying river mechanics, hydrology, everything about fluids and fluid flow. So recognizing this expertise, the legislators called us to action. They said, could you help? And of course we said yes, we could. And they established the Iowa Flood Center and here at the university in the College of Engineering. Understanding the river network and its statistical and other properties allows us to build efficient and effective hydrologic models.
I'm looking into power law distributions to fit to flood data, and we chose power law because it has similar self-scaling attributes that river network topology has, and river network topology is what governs the transportation of water.
Over the years, we realized that we need an effective way of communicating our findings to the general public of Iowa. The internet, of course, that's the main vehicle to do this.
So we developed Iowa Flood Information System at the Iowa Flood Center. It's up and running for the last 8 years and serving the public of Iowa. IFIS is a one-stop web platform for communicating flood-related data and information, including flood forecasts, flood inundation maps, rainfall, and weather information. And it deals with large-scale data sets, so we are processing over 50 gigabytes of data per day and dealing with operating a flood forecast model that solves over 1.5 million differential equations to understand the flood conditions.
The Iowa Watershed approach is something that, that I think many of us have tremendous pride in here.
Floods don't really behave across neighborhood boundaries or city boundaries or county boundaries. They behave in watersheds. So if we want to understand how floods work, if we want to get in place solutions for floods, we should be doing that at the watershed scale as well. And so the Iowa Watershed approach includes fundamentally a new idea about what if we focus on implementations in the upstream areas that can result in reduced flooding downstream.
In the Iowa Watershed Approach project, we work very closely with watershed management authorities as the local governance structure. We develop a hydrologic assessment. We work with planning consultants to create a 25-year plan for the watershed. The watersheds have hired watershed coordinators whose job it is each and every day to wake up and make the watershed a better place. We work with voluntary landowners and the watershed coordinators to find suitable locations for conservation practices. And now across 8 watersheds, we'll be building $40 million roughly in conservation practices. And then from those projects, we use our monitoring equipment and mathematical models to quantify the benefit for the benefit of these conservation practices on reduced flood damages.
A lot of times we think about flood disasters in terms of how much water, or the degree of damage, or the economic cost. But what about the social equity implications? With social vulnerability research, a big part of it is understanding the processes, but another part is building quantitative measures that we can use to understand how bad the problem is.
Over time, we developed a very strong brand name. The state agencies contribute to funding elements of our system. We always tell them that because the federal agencies in particular are constrained in their mission by the acts of US Congress, we have more flexibility. So often if they have some ideas and they cannot act on those ideas, we can.
It's really amazing to be a part of something that's a lot larger than me and to be involved in research that could potentially really positively affect hundreds of thousands of people. No matter where my career takes me, I know that the Iowa Flood Center has helped instill this desire to be a part of important research or projects.
We plan to continue serving the people of Iowa. There are significant scientific and practical issues that we need to address. So if there is something that we can do here within the state, that we should take care of ourselves. And when it comes to flooding and hydrology, water quality, we absolutely have the right expertise.
My name is Reed Maxwell. I am a professor of hydrology in the Department of Geology and Geological Engineering here at the Colorado School of Mines, and I direct the Integrated Groundwater Modeling Center. The big question that I'm working towards is how much water do we have, how much fresh water do we have, and how fast is it being replenished? Groundwater is really hard to observe, it's really hard to work with. We have just these very localized places where we can drill wells in the ground and sort of see groundwater directly or observe its pressure and infer its movement. And then we have some very interesting and novel techniques to infer how much groundwater we have, either from changes in storage, from changes in the gravity vector from space, from satellite remote sensing. And we use a lot of hydrologic modeling, a lot of groundwater models coupled to land surface models to understand and bridge that gap between this small scale and this really large scale. We tend to be very focused on technical details and communicating with other scientists, writing journal articles. We have our mechanisms of communication, but they're very kind of inaccessible to the public at large. And it's really enjoyable to be able to communicate what we do to a broad audience. And, you know, school kids are awesome. Very astute. But why else? Where does water want to flow?
Education and outreach is a top priority for the Integrated Groundwater Modeling Center. When we go to these events and see the type of enthusiasm that we saw today, it really hits home with us. It really solidifies why we do what we do.
Today we were explaining different groundwater systems, kind of how groundwater flows and the negative impacts of pollution and the difficulty you can have extracting and treating that pollution. They really like it when we let them play the bad guy, and when we do that, we give them a syringe of dye and they inject it into our groundwater model, and they can see, they can see very visually this plume of what we're calling pollution, right? It's just a general term, and they really like that visual.
These education and outreach experiences are so important and can really be valuable to our undergraduate and graduate students here at Mines as well as other universities.
One of the things about Colorado that's kind of cool.
It really teaches them skills in communication, changing behavior on the fly, all kinds of skills that are really useful in science in general. What we're doing is we're really instilling the importance of this early in their careers in the hopes that they will continue to engage with their community going forward.
Thanks everybody for standing out in the snow. We're going to learn about volcanoes.
Today we make a trash cano by sticking a small trash can in a big trash can and basically letting liquid nitrogen boil and expand, and then it explodes water up into the air. And the kids freak out, the kids love it. There's water in the air, there's ping pong balls flying everywhere. It's a great thing for the kids.
I've never done a trash cano in the snow. It did create a few extra challenges, but it also created a lot of fun too. It's science in action. So we talk about volcanoes. A lot of kids haven't necessarily seen a volcano in action, but they can really relate to the boom and the explosion and this material getting thrown up out of something due to a pressure change. So it's now part of my repertoire. I've taken the show on the road a lot.
Now, another big aspect of our center is research. That's mostly federally funded, and mostly funded by the National Science Foundation.
So I'm an aqueous geochemist. My specialty is studying how water and rocks interact chemically.
My research interests focus on evapotranspiration in mountain regions.
I am really interested in how rocks break down or weather.
My interests in research are ground and surface water hydrology and the modeling of those systems.
We have a lot of people who do a lot of different things, study a lot of different areas of geology and geological engineering. So the center, I think, represents the best of what we have to offer in terms of collaboration and solving problems by using many approaches, many minds.
We have a small community, and so being able to collaborate with people across campus in material science and physics. I have collaborations with professors in all different departments on campus. Right before this, I was in a laser lab. And so you can't make those connections as easily at larger universities.
We also do a lot of continuing education, a lot of tech transfer between research that happens here at the School of Mines and other places, and industry, government, other agencies working and consultants working in practice who want to kind of keep up and keep current in a broad range of groundwater and hydrologic modeling.
We've really built a program that we can be very proud of, and we are very proud of it. And I think we have really high hopes for the future, great plans, and I think we can just continue to do really great things.
The Department of Earth and Environmental Sciences was born in 2012 at the University of Milano Bicocca. The strategy of our department is to develop and improve researches, maximizing synergies between the two areas of earth and environmental sciences. Our inter- and multidisciplinary approach is based on a threefold concept: understanding the mechanism influencing climate changes in the past, monitoring the present assets, forecasting future scenarios to evaluate the impacts of climate changes on the environment, and suggest effective mitigation actions. We aim at generating scientific knowledge, technological infrastructures, and advanced initiatives in education with positive impact on local, regional, national, and international socioeconomic realities. Our department includes 40 geologists, 20 biologists, 15 chemists, 5 physicists and 3 engineers, working together from glaciology to geodynamics through atmospheric chemistry and ecology.
The Geodynamics Group at the Department of Earth and Environmental Sciences investigates the long-term evolution of climate through a focus on plate tectonics. Sedimentary basin, mountain belts, volcanic arcs, oceanic ridges, they are all expressions of plate tectonics, and they all have a huge impact on the geological carbon and water cycles which control climate on our planet. We study rocks from within these environments through a range of disciplines and techniques because they are the fundamental archives of information, and we investigate these rocks through field observations, numerical modeling, physical and chemical laboratory analysis. This is also what we teach our students in the Geological Sciences bachelor, master and doctoral degrees. They learn how to read the rocks just like a book and obtain their information regarding the functioning of the Earth system and the evolution of the Earth.
A deeper understanding of past climate changes is essential to assess the impact of human activities on climate and anticipate future climate changes. Ice cores have become one of the golden standards in paleoclimate research, thanks to their ability to archive climate information, such as greenhouse gases, temperature and atmospheric impurities. And they allow us to study glacial and interglacial cycles. The focus of the glaciology and paleoclimate group of DSAT is the study of aeolian mineral dust deflated from the continents and transported to the polar regions. By looking at the geochemistry, mineralogy and microphysics of dust, we can get a lot of information about atmospheric circulation changes, dust sources and environmental conditions at the sources. All this information is then put into global climate models, which include also the dust cycle. The concentration of mineral dust in polar ice is extremely low, and particles are very, very small. For this reason, at the Eurocold lab of DSAT, we have dedicated environments and clean rooms where the risk of sample contamination is reduced at minimum.
In our department, we study the sedimentary record from marine cores, looking at assemblage variations of microfossils like coccoliths, silicoflagellates, diatoms and forams, and we analyze geochemical proxies in benthic archives like mollusks, corals and calcareous algae to reconstruct paleoceanographic and paleoclimatic changes at high resolution. An important expertise in our team is also related to seafloor imaging and mapping using geophysical data like bathymetry, backscattering and seismic data, coupled with underwater videos and bottom sampling to investigate geomorphic processes in the submarine environment and their interaction with benthic organisms.
We study the impacts of climate change on freshwater and terrestrial ecosystem and on biota. Lakes are extremely sensitive to pressures that operate at the global, regional and local scale, making them good sentinels of environmental change. We are studying the different pathways that cascading effect of changes in air temperature and precipitation have on water temperature and vertical mixing regimes. These trigger the distribution of nutrients, dissolved oxygen and other compounds in surface and deep waters, that in turn control pelagic food webs. We are analyzing the responses of aquatic communities to anthropogenic impacts to develop tools for the management and conservation of freshwater ecosystem. We are investigating the effects of climate and habitat changes and the introduction of exotic species on the ecology of population in order to propose effective measures for long-term conservation of wildlife biodiversity. We are studying how, in mountain areas, ice melting during war period can increase habitat availability and high elevation and across the tree line for alpine plants.
In our department, the atmospheric research passes through different disciplines. The main target of our research concerning the aerosol direct effect is related to the black and brown carbon aerosol. We developed an experimental method able to quantify in any sky condition the heating rate induced by light-absorbing aerosol. Our campus is the first site in the world where the heating rate of black and brown carbon is experimentally determined continuously in time. The experimental heating rate was measured from Europe across the Baltic Sea, the Atlantic and the Arctic Ocean, showing that the heat trapped in mid-latitudes can be transported till the North Pole, amplifying again the Arctic amplification and warming.
Global warming and other effects related to climate change, such as the increase of frequency and intensity of rainfall events, are expected to boost geohazards and have a large impact on water and energy resources. For monitoring, we are developing a new lab called GEMMA with advanced monitoring tools such as drones equipped with thermocameras, hyperspectral cameras, ground penetrating radar and a laser scanner. With this tool we can monitor and survey the effect of climate changes in alpine areas, the evolution of landslides and rock glacier, and the degradation of permafrost, which are very important for geohazards. We have developed numerical tools and strategies that we can use for the modeling of these effects and that we can test against laboratory physical models or real-world case studies. A good example is offered by the Gallivaggio landslides that occurred in 2008. We can use numerical models in order to replicate and understand the dynamics of these phenomena. This allows us to improve our forecasting of potential future landslides and geohazards in light of risk assessment and risk management.
We offer 6 courses, a bachelor and a master in environmental sciences, in geological sciences, an international course in marine sciences, entirely in English, and a master course in chemistry. And finally, a very interesting PhD program. Here students are an active part of the team and learn how to study the Earth system processes relevant to and responsible for the evolution of our planet and ongoing climate changes through fieldwork, laboratory activities and modeling. We are confident that our multi- and interdisciplinary approach will develop cutting-edge research in science, providing a 360 degrees understanding of environmental and climatic change.
The Department of Geosciences in Potsdam is the strangest department you will ever see anywhere in the world, because it's not just a group of professors who work together in the university. We have a unique situation where several external research institutes are also linked to us, and professors who are part of the university work in these research institutes, which means that our students have access to research facilities at the university, but also research facilities in external institutes. We have 30 such institutes linked to the faculty.
The disciplines that are present at the University of Potsdam are quite diverse, so it's pretty exciting to discuss research with colleagues as well. My research is earthquakes on volcanoes, and we also study volcano analogues and associated hazards such as subglacial floods. We work with arrays to track moving sources to record weak signals, and we also have exciting new instruments which are rotational sensors, and we can use them to combine them with a normal seismometer to hopefully get array-like results, and we're like one of the few groups worldwide that actually have these sensors.
My topic is geological remote sensing, and I am working with remote sensing imagery and Earth surface processes, ranging from optical data to radar data or laser data, and we are using all of those different techniques. And the combination of this makes it very unique to study the Earth's surface and understand, for example, erosion, debris flows, and the impact on the infrastructure characterizing natural hazards, understanding landslides, understanding the impact of earthquakes.
So one thing that I'm working on right now is combining both geochemical estimates of erosion rates, for example, with remote sensing proxies, and we're developing new remote sensing proxies that we can then validate with these geochemical methods. And that's one thing that's really great about the University of Potsdam, is that we actually have the infrastructure here to do both. We have state-of-the-art geochemical labs and also the computational power to process this data.
This institute is a unique place to work in because of this combination that we have of really top-level scientists with this setup of labs that are absolutely top level. My research area is trying to tackle the problems of what's happening at depth in terms of fluids involved in plate tectonics, involved in mountain building processes. And in the last years, we worked hard to make Potsdam a real hub for this kind of investigation.
I'm a structural geologist working in East Africa. I'm working on extensional tectonics in the East African Rift, more specifically in Kenya. And I study the extension of the rift, and we use drones to generate high-resolution elevation models. And we have basically drones and survey equipment for every different task we need.
What is great at the University of Potsdam is that we focus in various applications. So we can develop our methodology to many topics. Here we have actually the instrumentations, which is state-of-the-art. For example, with the georadar, we send an electromagnetic pulse inside the ground to detect structures. And with students, we try to develop and to explore new ways to collect the data to get more information into, for example, archaeological targets or water content in the soil.
The 3D capabilities that we have here are for visualization and for analysis, meaning that we can dive into the three-dimensional world in that way, and that we can perform analysis on the point clouds as if we would be in the field. So it's both for educational purposes, that we teach the future generation how three-dimensional structures look like, but also for analytic purposes. The Institute of Geosciences has 120 incoming bachelor students every year, and we have about 20 master students starting every year, and we have a large number of PhD students, more than 50 PhD students that are currently at the department.
My research project is carbopaths, and we are focusing on carbonates at high pressure and high temperature using different high pressure techniques. It's really nice to do the PhD here because we have a laboratory full equipped for doing this kind of research, but also we are close to different institutes that can allow us to expand the data or the experience that we want to do.
I think the University of Potsdam is a great place to study because the University of Potsdam has a lot of instruments that are vital for field research, like for example drones or GPS instruments that we need to, if we go to the field, to collect high precision GPS points or drone data doing drone flights.
Innovation in teaching is a core feature of our faculty, always has been. Research-based teaching is what we do. Every student at bachelor level is involved in a research project of their own. Every student at master level is involved in a research project of their own. Fieldwork is core, laboratories, so that we can actually get all of our students to actually be involved in measuring things themselves.
I would like to have the future generation of students understand what it means standing in the field and reading the rocks, but also being able to quantify processes using modern remote sensing data. The other thing that makes it unique is that this is a growing university with still lots of potential for growth, and that makes it unique to establish a strong geoscientific educational program.
The School and Observatory of Earth Sciences of Strasburg has three main missions: teaching, research and observatory programs. Our five main themes are continental lithosphere dynamics, water resources and fluid circulation, especially in the context of global change, reservoirs and in particular geothermal resources, lithosphere dynamics, especially earthquakes and seismicity, finally deep earth and its structure and processes. We record and provide geophysical and environmental data from metropolitan France and from other places in the world, including Antarctica, in many different fields. These include seismology, magnetism, gravimetry, geodesy, and environmental geosciences. EOST hosts bachelor's, master's and PhD programs in many earth science fields, including geology, geophysics and environmental geosciences. We run the only French engineering diploma in geophysics. This involves theoretical and practical teaching by industry and academic experts. So the university campus here is extremely dynamic and is very beautiful. The same can be said for Strasburg itself. We are located in the center of Western Europe, and so very close to other universities in France, Germany, Switzerland, the Netherlands and Belgium.
Our research addresses how the Earth's surface evolved through geological times and what are the drivers of these changes. The surface of our planet is highly dynamic because the Earth has moving tectonic plates and it hosts an atmosphere, biosphere, cryosphere and hydrosphere. Climate is a major driver of environmental changes as illustrated by the dramatic shrinking of Lake Chad in the past, today and maybe tomorrow. Geologists find evidence of ancient ice sheet over Africa. This shows that continental drift also drives changes of surface, but at geological timescale. Landslides are both a process that shapes the Earth's surface and a geohazard that cause risks and damage to the society. The precise timing of the evolution of continental environment is a major issue. That's why we are running a lab of geochronology using cosmogenic isotopes and uranium series.
In a context of global change, we investigate alteration, weathering, and water transfer processes in continental hydrosystems. We develop multi-scale biogeochemical and isotopic approaches to understand mechanisms and processes in the critical zone. Specifically, we focus on 4 topics: the processes and reactions that determines the properties of water-mineral interface, the history of formation and evolution of alteration profiles, the exchange and transfer between soil and vegetation, and the transformation and transport of micropollutants in soil and at the catchment scale. We benefit from the technical support of Biogeochemical Analysis Center dedicated to soil and water chemistry, fluid mineral interfaces, and isotope measurement. To evaluate and predict fluid circulation and water resources, we combine laboratory experiment with field experiment, especially on our observatories, monitor for more 35 years for the Strasburg catchment in the forest and for more 20 years in the vineyard catchment of Rouffach. The development of hydrobiogeochemical model includes advanced computational techniques, inverse problem, and uncertainty analysis.
A key question in earthquake science is to understand what controls the behavior of active fault systems, what regions are prone to experience large earthquakes, and the problem is that fault processes span a very wide range of timescales. Now, a recent game changer is the explosion of near-fault observations, which is a new opportunity to better capture the accumulation of strain over centuries, over decades. Over much shorter timescales, we can also combine various datasets to constrain how this accumulated strain is then released by earthquakes or slow slip events. We can also investigate links between magma and the activation of faults or earthquakes. For example, we can use new earthquake detection location techniques to track how magma migrates in volcanoes.
In the Alsace region of France, we're very, very proud of our history of geothermal energy exploitation. Since the 1980s, there have been many wells drilled into the area, some of which are as deep as 5,000 meters. The reason why there's so much geothermal energy in the region, or energy exploitation, is that they are exploiting a thermal anomaly and also a hot natural brine within a fractured and therefore permeable granitic basement, which acts as the geothermal reservoir. We work very closely with French geothermal industry. Geothermal research is also funded by the National French Research Agency. I work in the rock deformation laboratory to supply rock physical properties of the geothermal rocks of the area, to inform on numerical modelling, heat flow modelling, for example. Our strength measurements in the lab can also help with borehole stability assessment and also stimulation strategies.
Accessing the deep Earth interior is difficult from the surface, so we need continuous and precise observation. At AOST, we have developed seismic tomographic techniques that provide us with quantitative image of the lower mantle. We can also use some gravimetric and geodetic and magnetic surface observations. So for instance, from magnetic observation, we can reconstruct core flows at the core surface. Going deeper into the Earth's core is more difficult. The inner core has some oscillations that we have never detected till now. Gravimetric, magnetic, seismological and geodetic observatories are all very important to have a chance to detect small signals coming from the Earth's deep interior, and particularly global coverage is very important. So stations like the one in Antarctica are fundamental in our research in the deep interior of the Earth.
In conclusion, we conduct innovative research in geosciences, especially looking at the links between deep earth processes and surface processes, natural hazards, natural resources and environmental geosciences. We provide a unique international teaching environment that combines university programs, an engineering school, and doctoral programs with very active research teams.
We want to know how our planet is changing, to understand different processes, different chemical reactions, and how the system all work together to make a sustainable planet for humankind.
We hope to help citizens figure out how to adapt to the climate change that's already here, but perhaps most of all to mitigate it, to transition out of the fossil fuel age to something better.
The choice we make can impact the generations to come. If we can all work together, we can solve the problem.
The Center for Global and Regional Environmental Research was started in 1990. A group of faculty, maybe a dozen or so, had been meeting and talking about this new idea that we could actually be changing the climate. Out of that, the state legislature decided to fund a center looking into questions of climate change, funded by a tax on utilities in the state. We use that to be a research center as well as do education and outreach to the citizens of Iowa. This is the 8th Iowa Climate Statement. We try to get all the scientists to agree on a climate statement that's unique to Iowa, that helps to inform policy in Iowa, also helps to inform citizens about what climate change might mean. We're going to experience much, much warmer conditions, much more severe flooding.
The Iowa Climate Statement is a good way of building consensus among scientists and then communicating that information more broadly to the public. If we're able to start to show Iowans how our local climate is being impacted by climate change, hopefully that will start to spur some local action to make a difference.
The mission, I would say, is to foster interdisciplinary research, including all aspects of sciences, both the natural sciences, the engineering, social and behavioral sciences, and even humanities. Most of our center does mathematical modeling. In my own case, modeling of agricultural crops and soils and how they are responding to climate change. But experimentally, we try to remove carbon dioxide, greenhouse gas from the atmosphere.
I work with high-protein microalgae, and I'm growing it to be a sustainable cattle feed. In this case, this is a resource recovery project. Microalgae is something valuable that we're growing, but we're growing it with simulated power plant emissions. The microalgae is capturing the CO2, it's something that's not being emitted.
My PhD research is about how we can use plants that accumulate a lot of nickel to make other useful materials, like energy storage materials or wastewater treatment materials. Places that have been polluted with metal, we can actually take the metal out of the soil and bring it back to a more natural state.
My overall research area is in developing sophisticated models that can be used to analyze air pollution. The real focus on climate change has been greenhouse gas emissions. But it turns out that aerosols, these particles that are air pollutants, they also play a tremendous role in climate system. Black carbon, coming from diesel engines or forest fires, they actually absorb solar radiation. So they act like a greenhouse gas. Where we have air pollution and weather in the same model, we can find that the black carbon, say in a city like Delhi, because of its warming agent, makes the atmosphere more stable and can actually increase the pollution levels because the emissions are not mixing as high into the atmosphere.
What I'm doing is called smoke plume rise. We calculate the injection height and then the model releases the fire emissions in this altitude. Models that don't include this parameterization, they release all the fire emissions in the first layer of the model. This contributes to inaccurate episodes of air quality.
The weather prediction, while they are getting more and more accurate, there is still room to be improved. For example, we don't know how accurate is our weather prediction in the rural areas. We are designing a meteorological sensor that is only cost $80. Local sensor help us to improve our understanding of satellite data, to what accuracy they have. On top of that, it also allows us to engage the citizen. We basically give those sensors to our citizens. Another part of the research I'm doing is also about the air pollution versus health.
I'm working on a new satellite mission called a Maya, multi-angle imager for aerosols, to study different type of particular like a matter pollution and their association with like a human health, like a respiratory disease, etc. We have like 11 cities like around the globe, so it's very, very cutting-edge research. Everybody works really hard and everybody strives to be the best. So we kind of push each other to be the best, and the staff here at Seeger, they are very supporting.
I think that the students are really exciting to work with because they get it. They realize that we have to respond to this challenge. We must change, and in the course of doing so, we can create something positive and an engine for economic development in the future.
The Department of Atmospheric Sciences is part of the School of Earth, Society, and the Environment and is within the College of Liberal Arts and Sciences. The Department of Atmospheric Sciences' vision is simple but all-encompassing, world-class learning and discovery in the atmospheric sciences. To this vision, we teach and conduct research in areas ranging from atmospheric chemistry and aerosols, climate and climate change, cloud physics and radiative processes, convective cloud dynamics and modeling, extratropical cyclones and precipitation, hydrometeorology, hydroclimatology, radar and satellite remote sensing, tropical meteorology and hurricanes, and finally, weather and climate risk.
I am a hydroclimatologist and a hydrometeorologist, so that means that I study the interactions between the land and the atmosphere. What we're trying to do is to understand how deforestation of the Amazon forest could affect hydroclimate over the entire continent. And with help from the National Center for Supercomputing Applications, we visualize this water vapor. My group is particularly interested in extreme events, and I'll give you the example of the Relampago project. My team was the hydrometeorology team. We were measuring the floods, and to do this, we used an instrument called acoustic Doppler current profiler. These boats that you use to traverse along the river, and that's going to give you stream flow.
I study all kinds of different cloud systems around the world. We started in the tropics and go all the way up to the mid-latitudes to try to understand the role of clouds and precipitation in the Earth system. The Relampago field campaign was a field campaign that occurred last spring and summer in the Southern Hemisphere in 2018 to study what we think are some of the deepest and most organized convective systems in the tropics. Our group uses a lot of satellites to measure cloud systems all over the tropics. Being on the ground is really important as well because we can observe the systems with very detailed instrumentation like ground-based radars. The University of Illinois has a wind profiling radar system to measure the wind above the site. It also lets us look at precipitation microphysics, and that helps us constrain models that help us simulate heavy precipitation or different types of clouds that develop different roles in the climate system.
My research focus is developing numerical models that simulate the evolution and the impacts of aerosol particles in the atmosphere. One important metric that we try to capture is the sizes of the aerosols. So there are different instruments that are basically sizing the aerosol particles. But then the other aspect, it's not only size, it's also composition. Some particles form droplets more easily than others, and this has to do with the composition of the particle. Similarly, with the modeling, we need to capture the same properties when we model aerosols as well, so size and composition. And that is challenging because each particle is different, and so that's one of the reasons why we developed this very high detailed aerosol model where we can look at individual particle compositions and track the particles as they are moving through the atmosphere.
My science focus is on climate science, climate modeling, and uncertainty quantification. For the most part, we study how the climate system is changing and what are the impacts for natural and human systems. Some of the climate models we use are very comprehensive Earth system models. We use a model called the Community Earth System Model, which is a very high-resolution atmosphere model at a 25-kilometer grid spacing, coupled to a fully dynamic ocean model. So at these high resolutions, or at these fine scales, the model can produce its own tropical cyclones within the climate system. So what our simulations are finding actually is that there are very close connections between short-term extreme weather events and longer-term climate variability that we're really able to now understand and diagnose using these complex Earth system models.
I do a lot of papers, and probably about half my research is related to climate. The other half is related to atmospheric chemistry issues, air quality. We're trying to do our own part here at the university. I helped develop a new center, the Center for Urban Resilience and Environmental Sustainability. And CURES is really aimed at helping cities plan for their futures, being able to adapt to the changes in climate that we're going to see no matter what we do. We also, as a nation, need to be looking at how do we reduce those emissions that are occurring from fossil fuels. And so I'm also working with people on what kind of solutions might we develop there. Cities and states are still continuing forward. Industry is still continuing forward because they know they have to play a longer game than just one administration. But we do need to ramp it up. And so it's really important that we do something about these changes in climate that are happening.
Students here at the University of Illinois, we try to get them hands-on experience not only in the classroom, on computers and through data science, but also get them out in the field observing weather, because that's really where I think students really get the foundational physics.
We involve our students in all aspects of the research process. For an example, 9 of our graduate students participated in the Relampago field campaign. Additionally, 7 of our undergraduates spent their Thanksgiving break last November helping to collect data. Our hopes for the future is to increase the impact of our graduate program. So we're developing a set of online graduate courses as well as an online master's degree. We also hope to continue to enhance our research and teaching infrastructure. And finally, we hope to continue to take leadership roles in field campaigns around the world to lead high-performance computing initiatives and help with assessments of climate around the world.
Here we are on the conference floor asking attendees, what lessons have your work life taught you?
I would say that my work life as a scientist, and that being I'm a second-year master's student at the university I work for, has expanded my knowledge of how things are done in the scientific community, not just people publishing papers over and over that you read as an undergrad just to write a final paper, but the actual attention to detail that you need to have and the hardcore science that really goes into some of these research projects.
I've learned that whatever you do, whatever you're studying, it has to be something you like. You go after whatever personally fascinates you, even if it is or isn't what you're necessarily being tasked to do. You have to sometimes go sideways to find something worthwhile and exciting.
In my work life, I've learned that it's really important to communicate your science. And I run a program called the SOARS program, which is Significant Opportunities in Atmospheric Science and Research and Science. And students can come multi-years, up to 4 summers, and they actually have to communicate their science.
I'm a geoscientist and I've learned an awful lot about the Earth. I've learned how much fun it is to work with other geoscientists, and I really enjoy these meetings.
What I've learned is that you have to follow your passion. That when something is exciting and new, it brings you so much joy to be the first one in the whole universe to know something. And I've been counting electrons and protons in space for 43 years, and it still surprises me. And so I think you have to keep that open mind, that spirit of inquiry, so that when the right data comes along, you'll know what it really means.
Joining us now is Evelyn Valdez-Ward, and she is PhD candidate for the University of California at Irvine. And thank you for joining us.
Thank you for having me.
Well, let's begin. What is AGU's Voices for Science?
So the Voices for Science program is both a science communication and science policy workshop in which a lot of geologists from different levels in their career, whether they be grad students or further along tenured faculty or working in industry, come together and we talk about how do we improve the scientific field through science communication and science policy. And so AGU gives us this training, and what's nice about it is that we get to interact with a lot of different people from all over the nation who are interested in improving the sciences, but especially the geosciences. And so together through this workshop, we work on projects together, we get training, whether that be written trainings for op-eds, podcasts, interviews. They teach us a lot of different things on how to engage with lawmakers, how to inform policies. And it's just a really great program, especially if this is your first time and trying to go beyond just the research lab and bring your science out into our public, into the nation, and improve the geosciences as a whole.
And this is part of a Centennial Grant, correct?
Well, the work that I'm doing in particular was funded by the Centennial Grant, and in addition with Voices for Science.
And what do you do particularly? What is your focus?
Yeah, so my workshop that we created, and it was inspired by Voices for Science and a lot of science communication trainings that we went to, is called Reclaiming STEM. And it is a science communication and science policy training that's specifically for marginalized scientists and created by marginalized scientists. So we bring together the worlds of science policy and science communication, but to advance social justice. And we really focus on early career scientists, so scientists whether they be in their undergrad or graduate programs, postdoc and early career faculty, and we come together to talk about how can you use your science to advance social justice. But more importantly, bringing all of your identity so you can bring your whole self and not have to feel ashamed or have to feel like you have to hide parts of yourself, and really just creating this safe and brave space where we all come together, we talk about what it's like to have a lot of intersectional identities within STEM in particular, and then how do we improve the world of science as a whole.
And why is this initiative so important?
So the science communication workshop is really important because a lot of the science communication trainings that we go to tend to lack diversity, and a lot of the science communicators also tend to lack diversity. And so a lot of the times the paths that they might recommend are not really feasible for people who are from marginalized identities. For example, a lot of science policy and communication internships rely on unpaid internships, and sometimes that might not be feasible for people who have dependents or maybe, for a lot of different reasons. And on top of that, there's just a lot of other social justice issues going on in the world right now that we can't really advance our science without also addressing, for example, immigration reform or working with queer communities and that kind of thing. And so for this community to come together from all diverse identities, it really gives you more of an insight into what the world can be within science, and it's just not all the same kind of people doing it.
All right, well, we wish you future success, and thank you for your time, Evelyn.
Thank you.
Joining us now is Vijay Limaye, and he is a Climate Change and Health Science Fellow with NRDC. And thank you for joining us.
Thank you.
Why don't you tell us about your recent study that was published in GeoHealth?
Sure. So when we think about climate change and the damage it inflicts on Americans right now, we hear a lot about property loss, crop failure, or damage to homes. We hear a lot less about damage to human health, which we know is extremely profound and extraordinarily expensive. So we looked at a case study set of 10 climate-sensitive events that hit the US in 2012, which was actually the hottest year the country's ever experienced. When we looked across those case studies, everything from extreme heat to ozone air pollution, an outbreak of West Nile virus in Texas, or wildfires raging in Colorado and Washington, we came up with an estimate of about 900 deaths and tens of thousands of expensive hospitalizations and emergency room visits. So when we added up the health costs of those impacts, we ended up with a $10 billion price tag just from a subset of case studies that hit the US in 1 year.
So why are these studies so important, and what do you learn from them to move forward as we approach 2020?
Sure. So, we have seen that the health costs of climate change have really been left out of our public understanding and policymaking on climate change. When we think about the health costs and add those into the climate damages that we're seeing across the country, we end up with even more reason to act now in order to avoid suffering and avoid expensive costs. Right now, we know that more than half of American adults struggle to pay their medical bills, and climate change is only going to make that problem worse if we fail to act. So we really need to take advantage of the science that's published in the GeoHealth Journal as another reason to cut carbon pollution and prepare for climate impacts.
Right. Well, looking down the road, what are some of the health repercussions?
Yeah, this year, in the last few months, we've seen raging wildfires in California, which is an underappreciated health risk in terms of wildfire smoke that can actually travel hundreds of miles downwind and inflict harms on millions of Americans. That air pollution is deadly. We know that air pollution in this country kills more than 100,000 Americans every year, and wildfire smoke is making it harder to breathe on the West Coast, but in other parts of the country as well, causing extremely expensive and damaging impacts to human health. So when we look into the future in 2020, we're faced with, in the near term, the hottest months that we've seen in recorded human history, which certainly poses risks for heat waves, but also other climate-sensitive events like wildfires and air pollution.
Any day in and day out solutions that we can all do to help?
Absolutely. We need to be talking about climate change as a health problem. It's estimated that only about 1% of climate research is actually about human health, even though we know that the life of everyone on this planet, including young folks right now, will be affected and in some ways defined by this problem. So we really need to be talking about climate change and link the expensive suffering that we see every day in the headlines to the need for action on this problem.
Absolutely. Vijay, thank you so much.
Thanks a lot.
That's it for today, but we'll be back each day of the meeting with more exclusive material. See you tomorrow, AGU.